So, like I said, this is sort of a one more derivative rule because this sets up a function, just a differently defined function that we're used to. It's an accumulation of area function. Right? So as I move further out, under this I accumulate more area. I could go below the x-axis, which is negative area, I'm losing area, but it's how much area I'm accumulating as I'm moving along in the x direction. So it's its own function, so we can kind of analyze it by itself. But the more important thing this does is it kind of sets us up to be able to do the really important thing, which is really connecting integrals and antiderivatives. Because then finding the area under things is going to be just as easy as first finding the antiderivative and then plugging some stuff in to see how much area there is. There's two kind of main approaches to take to show this. This is going to be the fundamental theorem of calculus part 2, amazingly enough. There's only 2 parts, so don't freak. One kind of, admittedly kind of weird kind of way to do this is, let me start off with the result, sort of. Let me write it in kind of a strange way, but we'll see why. Is this the way I wanted to do it? Yeah, this way. Okay, let's analyze what this means. By the way, let me say a couple things on the side here. Big ass F is an antiderivative of little f. So whenever you see a big ass F, normally that's meant to imply that it's an antiderivative. So big G would be the antiderivative of G, little g, unless it's otherwise stated in the problem or something. Right, so sort of the notation we use, it's sort of like an answer to prime notation. Now I'm unpriming something, I just kind of make it a capital letter, right? So do we make it an even bigger F if I do another integral? No. Which means, and remember, recall G prime is equal to F, which meant that G equaled F plus a constant. Okay. We're good so far. So all that stuff we talked about earlier, I really hope it can all be pieced together for you. So that means then that this is the integral from a to x2. We got it. This is equal to, so let me put one last thing, hopefully, I don't know if you guys can put this connection, but that means that this is equal to this off by a constant. Of course I did that. What should this be? Yeah, that's why I thought I didn't write it yet, because I didn't. So I anti-derive this side, I should anti-derive that side. So they're off by a constant. So then this is G of x2 plus a constant. Remember, what would G of x2 mean? It would mean the area under the F from A to x2. Stay with me. Minus the area under from A to x1, F of t dt, plus a constant. So what happens to the constants? They cancel each other out. And you're left with integral a to x2, f of t dt, minus the integral a to x1, f of t dt. All right. It's kind of a new way of explaining this that I'm trying to come up with, but then I'll show you the old way. Nothing wrong with the old way, really. Just want I'll show you multiple ways of seeing this. So that basically means the area up until x2, and that basically means the area up until x1. So it shouldn't be that big of a surprise that I can do something here. What did you guys see something we just learned today? What can I do here? Look how they both agree on the A. If I wanted to switch these, then I could actually do something with them. Then I can kind of put these together. Just to remind you guys. Side note, if I have integral a to b of f plus integral b to c of f, what does that become? Think about what this means. I'm going from a to b, and then I'm adding to that the area from b to c. So of course it's going to be a to c, right? Okay, that's something we've talked about before. You guys were looking a little bit like, what the hell do we do with this shit? Now, do you see how the B part is there and there, so it kind of connects here, so I'm able to go from A to C. It makes this connection. A to B, B to C, there. Then I can go straight from A to C. So what's wrong over there? A couple things. Well, there's one thing that takes care of two problems. One thing is, this is not a plus, but the other thing is, this is kind of in the wrong order. So if I change the order, I change the sign, don't I? So this would become integral a to x2, f of t dt, plus integral x1 to a, which doesn't, I know from your perspective, you're like, wow, Jeff, that was amazing. But now these are in the right place to connect. So now it goes from x1 to x2. So x1 to a added to a to x2, well then just freaking get the area from x1 to x2. Why do that middle dude? So now this is equal to area under the curve from x1 to x2. So what have we just shown then? Let me write this the right way around. I kind of started with the result, and I like this kind of way, but so the integral from x1 to x2, f of t dt, equals f evaluated at x2 minus f evaluated at x1. All right, now let me write this in a better form. I sort of had to do this to keep the t notation to make the connection with stuff we were doing earlier. How important are the variables that I choose to designate the axes? If it's time, what would this one? This would be t. If it's, I don't know, if it doesn't matter, then I can make this x. If it's number of watermelons I eat, it could be w-axis, right? The number of watermelons and how my stomach feels or something, right? You guys kind of with me? So so I can rewrite this. What is x1 and x2, by the way? When I put a subscript on there, that means it's what? What does the subscript mean? And whenever we use subscripts, we're trying to say it's a specific thing. It's a number. It's, I know x can be any number, but this is some specific number that I'm working with. Sort of like in the slope formula, x2 minus x1 on the bottom. This means it's the x pieces of the points I'm looking at. Not just any x I want anywhere. So I can rewrite this in this form. From one number to another, f of something d that thing is f of the top minus f of the bottom. So what this really says is, to find the area under a function, I can just evaluate its antiderivative at the endpoints and take the difference. All right, let me say this again, because this is like monster thing. To find the area under a function. And if that function was ugly, we'd have to do it with the limiting of the rectangles, and oh my God, that gets really disgusting very fast. If you've done your homework or were here for the other day and you saw that happen, you're like, I agree with you so much. But now it's just find the antiderivative and evaluate it at the endpoints. Yes, sir?
So two different things. So the constants won't matter because they're being subtracted from each other anyways. So
beautiful. That going back now, that makes complete sense out of F-Talk 1, why it didn't matter which one you picked. But
for the second part, when you chose to flip the second one, just to cancel the negative, you could have flipped the first one.
Totally. Yeah, because then it would have been negative f of a minus f of b, which would have become this. Yeah. But it just was cleaner to pick the other one. I love it. Okay, okay. Let me show you another way to look at this, and then we'll do some very, very concrete examples. This is going to feel in a few places the same because it's proving the same thing. Let me just start off by some ground stuff. Go ahead. Okay. And then over here we know that f of x is g of x plus c. That's an idea we had earlier. Same idea from before. Let me write down here, since g prime is f of x. Okay. What is g of a? What would g of a be? We've done something like this before. Yeah, if you just put it in, where's a go? So it'd be a to a of, who cares, is 0. There's no area if you don't go anywhere, right? What's g of b? Just in symbols. I mean, it's not going to be able to do anything. What would g of b be? What would g of b be? It'd be a to b f of t dt. No big deal, right? I just want to set that down. So g of a is this. G of b is that. Okay. Now, if I look again at this, it's a little bit cleaner because you got your a's and your b's. You might see why I didn't want to use a's and b's doing it the other way. There's already an a in there and stuff. This is going to seem very familiar. Big ass f of b is g of b plus c. Big ass f of a is g of a plus c. Right, that fact is pointed out up there. G of b is this guy. C's cancel and g of a is 0. So again, kind of a different way, but really if you look at it, the math is almost the same. But it's a very kind of different way of looking at it. Either way, they're both proofs that show you that to find the area under a curve between two given numbers, two given inputs, I just have to find the antiderivative and evaluate them at those inputs. So now that we got the formalities down, let me show you sort of a hand-waving thing. So we know that this is related to, basically means the area between up until b, right? This means the area up until b from something. F of a means the area up until a of something. Let's put a over here just to be. So if I take the difference of the two, I get the area between the two, which is the integral a to b. I mean, so that, you know, I can't say this is a proof, but now this is what those proofs are capturing the idea of. This is basically that. It's got the C in it, but oh well. The hand-waving thing I don't have to prove. That's the area up until B. That's the area up until A. Of course the difference is the area between A and B. Okay, like it. So let's do some concrete examples. Start off really nice. What was that? Here, let's do this. Yeah. All right, now watch this. What was it? 1 to 4. Remember this guy here, the one with the on both sides? We did this the other day. Remember that? 1 to 4. Where'd it go? Negative x squared plus 6x minus 4. Now, here's the idea. You're going to merge two things. 4.9 was all about finding antiderivatives of kind of easy stuff like this. How good are we now at finding these antiderivatives? I mean, if it's a power rule, which is really all this is, you raise the power by 1 and then divide by that new power. That's the rule, right? The rule is you raise the power by 1 and you divide by that power. And of course, let's see. Now what's going to happen every single time if I write the plus c's? If it's the f evaluated at 4 and the big SF evaluated at 1 subtracted, the c's will always cancel. So when you have what's called a definite interval, it's got defined endpoints. If I had no numbers here, that's what's called an indefinite interval. I'll have to look at that later. If you have a definite interval, those c's are always going to cancel, so there's no need to write them. What is this guy's antiderivative then? Yeah. So this goes up to the third power, so you divide by 3. I like it. I really want to make sure you guys, what's the derivative of this? It would be multiplied by that power and then take the power down by 1, right? So this does the exact opposite. Take the power up by 1 and then divide by that. It does everything the opposite order, the opposite way. Plus, this one is nice.
3x squared.
Yeah, it's got the 2 factor that goes back up, so 3x squared. And this is always nice. 4x. And here's the notation that we write. We did the antiderivative. What symbol would this have if I wanted to give it a symbol? Big ass F. All right, that's the antiderivative of this. And I want to evaluate, here's the way we write this. Evaluate it from 1 to 4. That's what that means. So I'm not done with the problem yet. I have to evaluate this from 1 to 4. Why didn't I write the plus c? Because they would cancel anyway. And now I just got to throw the 4 and the 1 in. So you get negative 64 thirds plus 16 times 3, 48, minus 16. So that is f evaluated at b. That's big ass F evaluated at b. Minus big ass F evaluated at a would be negative 1/3 plus 3 minus 4. So one big mistake is people forget to bring that negative through. So you get plus 1/3, so you get negative 63 thirds. Is that cool? Negative 64 thirds plus 1/3. Here you get 32, and then here you get minus negative 1. Is that decent? I put my thirds together because now I got a nice number. Do you guys still have this? Do you guys still have this? Anybody? Do you remember the number we got? The real one? The one we got out of the calculator? The one we got out of the calculator? 12. All right. So this is negative 21 plus 32 plus 1, which is negative 11 plus 1, which is 12. Sorry, not negative 1, but 11 plus 1 is 12. So we just did what the calculator did for us the other day. We can do it now by hand. Because we finally married the two ideas. The relatively easy idea at the moment of antiderivative with the idea of area. Yes?
Negative 63 over 3?
Oh, negative 64 thirds plus 1/3. Just throwing my like terms. Yeah. All right. Here, before we do another concrete example, I want to show you another reason why these should be connected. Let me write this like this. If I write this like this, let me see how much I throw you guys off. What should that be? Don't overthink it. So if I write like this, the answer is big ass f of x plus c. Right? Because now we know that integration is related to antiderivatives. So if it's already, this would just, so what it does is, f becomes big ass F because there's no primes to take away. I'm undoing the derivative. So if I undo this derivative, this just becomes this, right? Okay, I like it. What would the integral of velocity be? What should it be? Position. Right? Plus some c. Because it kind of makes sense. If I notice how this, remember, taking the areas is multiplying. So if I had, I really want this to make sense. If I had a function that was my velocity, and I had it between 2 points, right, A and B or whatever, wouldn't this be time, right? This would be change in time. And of course, this is change in position. That's what velocity is change in position. That's why velocity is the change in position over change in time, right? So if I do, what do I get when I multiply velocity times change in time? I get what? What do I get when I multiply velocity times change in time? So if you're going 80 miles an hour and you let 2 hours go by, how much is your position changed? 80 miles an hour for a couple hours. How much is your position changed? If you're going 80 miles an hour for 2 hours, how much is your position changed? 160 miles. I like, right? Right? Okay. Again, I love you. You're all like, that was way too easy, dude. You're talking about weird shit, and then you want me just to do 2 times 80? No. So what is velocity times change in time? It's a change in position. So when I integrate this, I don't get really my true position. That's why there's a plus c. I get my how much my position changed, and the c is kind of like where I started. So if I knew my position changed by 3 meters, but I don't know where I started, I don't know where I am. The C needs more information. Where did I start? If I started at the 10-meter mark, now I'm at the 13-meter mark. That's the change in 3. And the reason that it makes sense that the integral should be the antiderivative here is you can see it really well with velocity and position. Well, the velocity, the position is the antiderivative velocity, and if you find the areas, you're doing delta t times delta v. That is going to give you change in position. That's just what it does. So I'm undoing the division that slopes do. What are slopes? Change in y divided by change in x. So what does integration do? It undoes that division, gives you back to what delta y was. It undoes that division by x. It's multiplying by that change. Maybe. So that's just another reason why it makes sense that this thing that's built off of areas should be related to the antiderivative. Okay, so let's do another concrete example, like this one. Let's do one with some yummy trig in there.
What section is
This
this?
is 5.3. Should be 5.3. Yeah. Yep, it's got all the F-talks in it. Let's see, let's not be too evil. There's one little thing you have to pay attention to. You either could use, you could try to use a trig identity here if you wanted to, but does anyone remember the trig identity for cosine 2 theta? So that may be one reason not to. You should know it, but another reason not to is it's not helpful here. What is the What's cosine 2 theta equals? Everybody know? You gotta remember this. It's cosine squared minus sine squared. That's the fundamental thing. And then it has two other ways you can write it. Real quick. Cosine A plus B. Remember, cosine's an asshole. All right? So I just have a shirt that says, yes, I am a cosine. This is cosine A. So cosine is an asshole. It says, me first, screw you, sine. Okay, sine, go ahead, but I'm going to give you the opposite sine. Ha, 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 you suck. That's cosine being an asshole. Me first, me first. Sine would be sine and cosine is both take. Oh, let's do it. Just keep the sign the same. You know? All right? Good cop back up in my head. Now, so what about 2 theta then? Well, that's theta plus theta, right? 2 thetas, theta plus theta. That's ground shaking. So what do I get? Cosine theta, minus sine theta, which is cosine squared theta minus sine squared theta. And of course, cosine squared theta is 1 minus sine squared theta, so you have another way to write it. What do you do? Does this hopefully sound somewhat familiar, kind of? If you've never taken trig, what the shit are you doing here? Number one. So you must have taken trig. So this must sound vaguely familiar. But why would that not help me? What do I take the derivative of to get cosine squared? You don't know. You don't. Don't think you do, because you don't. You can't, if I try to integrate cosine squared, you cannot say that equals sine squared. Because when you take the derivative of sine squared, you don't get cosine squared, so that can't be true. You guys understand? You can't take the integral of a piece of something and leave the other piece alone. You cannot do that. Integration is much more difficult than the derivatives. It just is. Not always. This integral is not as bad as it seems. Where's cosine come from? What do you take the derivative of to get cosine? Sine. So it is sine 2 theta, but there's something missing, because what's the derivative of this? Cosine 2 theta times 2. Is there a 2 here? So what must have been here so that 2 would have canceled? Over. Yes, over 2. And that's got to be evaluated pi over 2 to 5 pi over 6. So here's the next big thing, and we're just getting into this, so I want you to always know the right way to do this. You always put the top one in first minus the bottom one in. You don't get to choose which way. Because you always want to go further, subtract. You want to go further and then subtract the closer one to get what's in the middle. So you always put the top one in first. So you get, right, there's that, oh man, that works twice. Top first, okay. Sine twice this over 2 minus sine twice this. All right, did 2 different ways, over 2. What's this going to be? What's sine of pi? 0. So now I can focus on sine of 5 pi over 3. Write that as 1/2. All right, so finish that out. What is sine 5 pi over 3? Yes. Negative square root of 3 over 2, so you get negative square root of 3 over 4 total. 5 over 3 is 60-degree reference angle in the 4th quadrant. It's closer to the y, so sine likes it. It's bigger, it's negative, and then you cut it in half. Okay. So on one level, you really gotta like this, because I don't know what you were thinking. We were getting into areas, you're like, oh my god, this is totally unrelated to what we were doing before. If you've had any calculus, you kind of knew where I was going to like get there already, so I don't have to do any more of this weird little piddly limit summation stuff. But now you see the connection. Thank God. We did all that differentiation stuff. You should know all that really pretty well. And the better you know that, the easier this is going to be, because you're just undoing that. Now, I'm not saying this is always going to be easy. I can very quickly make this something impossible for you to do, like cosine squared, but even that's not impossible, because you just use a trig identity to undo that. But so very often it's either simplify what's in there, or use an identity for something in there, or you've got to learn a new technique, and there's a lot of techniques of integration. So if you have to take Calc 2, we're going to learn a couple of techniques in here, and then Calc 2, the very first thing, this whole chapter, just purely on other techniques based on what's inside your integral, what to do. So what if I had this guy here? Let's see, integral -4 to -2. Say 3 over x minus 1. I like it. Plus. Doesn't really matter. Oh yeah, cool. Let's do that. E to the negative x. Remember, you can take constants out of the integrals. So one thing you could do here, let me just show you, here's the first step you could take. To get the 3 out of the way, you can split the integral up across the two things. So here's one little thing you can do always to focus your attention. Focus your attention just on this, get the 3 out of the way. Plus the integral for this one, now you can focus on that next, right? You're not trying to think of everything at once. Remember, with that symbol, you're always thinking backwards. What function would I put here so its derivative would be what I see there? You think backwards because this is the inverse operation of differentiation. So who thinks they have what goes here? Close. There's a little something there. It's not this. Thankfully, because then my inputs, you'd start to wonder about me. If you haven't already started wondering. It's got to be absolute values. Remember that little thing we said about it's got to match the domain? And this is one place where that becomes very important, because otherwise I couldn't do this at all. Is 1 over x minus 1 cool with these and everything in between? What's the only place 1 over x minus 1 has a problem? 1. And thankfully that's not in there. If it was, if I went from -4 to 2 of this, you would say that's a improper integral. That's improper. I won't touch that. Does that kind of make sense? I knew that's a new word. It's going to come up soon, but that's what you'd say if it included something that makes the function itself go crazy. It's like, what's the area of this if it goes to infinity? Holy shit. It's not always infinite, by the way. But that just makes it match with the domain of this, which makes these possible. Because now I got to evaluate that from -4 to -2. Plus, what about this guy? It wants to be its own derivative, but the derivative would be, have a negative there, so you need to have a minus there so it'll kill it when it wants to come down. I always like to think about that. What extra piece would come up with what I've written down? What would I put there to kill it? Because I don't want it there if it's not there. From -4 to -2. So then I get 3 natural log of good, natural log of 3, minus 3 natural log of 5. I like it. I don't know why I put parentheses around there. You don't have to. minus e to the second power. Let me see if you guys are cool with this. I mean, here's where people make their biggest mistake. What should be the sign I write next? Or you can just do this, right? That would be e to the negative x negative 2, bam, minus e to the fourth, and then negative can come through. The biggest mistake is people forget that negative has to go through to both parts of that. How do I do this? It's that evaluated this minus that evaluated at this. And if there's a minus in front of all that shit, oh crap, it's going to make it a plus in the middle now. That's one of the easiest little places to make a mistake. Stupid little mistake that you wouldn't lose a lot of points on. And then you can distribute that. That's basically all I could do. I want to make this point really big right now. Nothing to do with any specific person. I was just reminded of this. This is a huge mistake. This is crazy huge. And when my Calc 3 students were making this mistake, I wanted to whack them on the head, but I couldn't. Instead, I just cried. What is this? What is this? This is nice.
ln.
Yeah, ln, absolute value x, plus c. You know, all totally official and all that kind of stuff. What's this? It's not, it sure as all hell is not ln of x squared. It is so desperately not that. Because I can write that as x to the negative 2. Yeah, negative x to the negative 1, so negative 1 over x. So what is the only thing? What's the derivative of natural log of x? It's 1 over x. So what's the only time that the answer to an integral is going to be ln is if it's a first power dude on the bottom. That is the one place that this rule craps out. This rule says raise the power by 1, divide by what you get. Well, if the power is negative 1, when you raise the power by 1, you get 0, and divide by 0, oh shit. Right? So the one place this rule does not work is when n is negative 1. But thank God we know what that is. If n is negative 1, it's ln. It's got its own little rule, because that's what ln, it's one thing it does. Bridges that gap. It fills in that hole there. Okay. So let me show you something. Let me make sure you understand this connection here. And then we might do, yeah, we'll do a little bit more. Where's the next thing? Oh yeah, cool. I like it. Where'd he go? Real quick, what's this guy's derivative? Almost. Left off one thing from what I heard. So it'll be over x squared minus 4x, right? Times the derivative of x squared minus 4x, which is 2x minus 4. I don't know. All right, is everybody cool with that? We stop right there. Right? It's 1 over the thing inside times the derivative of the thing inside. Good old chain rule. Get rid of that. Sorry. Get rid of that is that over this. Okay, so what is this integral then? Bless you. Right? So, I mean, you can't. So, if you do the derivative of something and then they ask you for the integral of your result, then of course you know where it came from, right? You just did it. You can't do that for everything, though. But do you see how if I ask you what the integral of this is, you cannot currently do it because it is missing something. It is missing the chain rule piece. So we cannot do this at the moment. Well, we could. We could use partial fractions on this, which we need to review. Anybody know what I mean when I say partial fractions? You're like, you do know what I mean, but they're horrible. So we'll review partial fractions. I'll try to make sure you see how they're not horrible. I can understand how they could seem that way. Partial fraction decomposition is something that should have been covered in pre-calc, but I just found out that some teachers maybe didn't cover it, which is really effed up, because it is pre-calculus. Okay. So last thing for today. Oh, let me see. Oh, page 403's got a nice big table of integrals you can reference. I'm not going to make you know the hyperbolic stuff. I think I told you that before. Blah, 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 blah. Let me see if they have anything different in here. No, okay. I lock it. So here's a different kind of problem. Here's kind of a conceptual problem that I like to give. If this is the rate of growth of a child in pounds per year, what does this mean? Yep. So this would be the rate of change in weight times the time. That should be the total amount of weight gained from age 5 to 10. Now, can you tell me how heavy the child is? No, because this would be W of t plus some c that I don't have enough information to figure out, right? Now, it is from 5 to 10, but it still is just going to be a change in weight, not their actual weight, right? Okay, I like it. So it's how much their weight increased from age 5 to age 10. I like it. Okay, so here, let me give you this. I can finally shut up. I think I've told you enough stuff. Here's a little review of everything in Chapter 5 that we've done so far. So give these a try, then we'll go over them, and then we'll